That's great.
No, we've got six.
Right.
No, six.
Six.
There's six post-class activities listed out up there.
Okay. Halfway.
There's definitely more than three. I can tell you that much.
Wait. Never mind.
We have 2 full weeks, and then we have Monday, Tuesday, and then exams happen Wednesday, Thursday, Friday. So, the Monday class of that Monday, Tuesday will be review day again. And then we'll have exam that really late Thursday time. So 3 classes this week, 3 classes next week, 1 finals week, and then the last exam.
There's no class on Wednesday.
Finals start Wednesday, so all classes come to an end that Tuesday. The last day of regular class times is that Tuesday. I kept typing it a bunch today. The 28th is the last regular class schedule day. All right. Any other clarifying questions on things? The next written homework should have been posted last week on Friday. I did get that done before I had it out. All right. Oh. Also, written homework from last Friday should be back now. So if you guys have any follow-up questions on those, let me know while I'm flipping through that. All right, so getting into our next section then. We have talked the last, I guess it's week-ish, because we had Easter in there, a little more than a week. We started off with the idea of the antiderivative in 5.1, which is what is a function so that when I take its derivative, I get this idea. So say capital F of x is the, say, derivative of f of x. The integral was finding, if I then want to find that antiderivative of capital F, it would be the function plus c. So we talked about that in 5.1. Then 5.2 and 5.3, we were finding areas with basic sums and then Riemann sums. Not a whole lot different between those two. Just names. And it was finding the area, and we eventually then put notation to it to say the area between 2 points would be this definite integral from a to b of whatever my function is. Section 5.4 takes those two things and says the antiderivative is also the thing that's finding this area. While these were referring to different quote unquote ideas of the antiderivative meaning undo the derivative, and the area saying find the area under the curve, they are referring to the same work essentially. And so 5.4 puts them together and says, if a function is continuous on the closed interval a to b, and capital F is an antiderivative of f, little f on the interval ab, then the definite integral from a to b of f of x dx says find the antiderivative and plug in b, then plug in a. And this will find the area under the curve between x equals a and x equals b. So if I'm given some curve f of x and I want to find this area, I can find it by finding the antiderivative and plugging in b and plugging in a. Let's actually look at some examples. If I want to find the area under the curve of 6x squared minus 3x from 1 to 2, comes down to steps of find that antiderivative, then plug in the bounds. So first, we'd want to find what is the antiderivative of 6x squared minus 3x. Two x cubed three over 2x squared. And once we take the antiderivative, we change our notation. We put a long bar at the end, saying from 1 to 2. Largely it's notation of, hey, I've taken the antiderivative. This now means plug in 2 minus plug in 1. Antiderivative rule reminders. We added 1 to the exponent, and then we divided by the new exponent. So 6 divided by 3 was the 2. Adding to the exponent, 1 plus 2 gave us 2. Divide by the exponent gave us the 3/2. Okay, so then plug in the bounds. We plug in the upper bound first. 2 cubed minus 3/2, 2 squared. And we subtract off plugging in 1. And then just evaluate and simplify down. So things like what is 2 times 2 cubed? 16. 3/2 times 2 squared? 6. 2 times 1 cubed? 2. And negative 3/2 times 1 squared? Negative 3/2. And what does then all of that simplify down to? Yeah. Yes. Should be. See, have calculator out, so I'll say confirm that. Should be. Or halves.
Is
Hmm.
is the thing on top both connected, or is that a different? Is that simplified? That's simplified. Oh, okay. So that's
Yeah, we're just looking for what is 16 minus 6 minus 2 minus 3/2 with parentheses in there.
I typed in the whole top thing and got 1.5.
This whole part, and we just got 1.5?
Yeah, I'm typing in the bottom part now.
Yeah.
That looks a lot easier.
It is, yes. My guess with the top is that something with fractions went off.
Yeah,
Yeah,
9.5.
9.5. Awesome. All right. So we get that process now, the fundamental theorem, take the antiderivative, plug in the bounds. So if I wanted to evaluate this, what would we do? Find the antiderivative of what? That function, the x to the 1/3. What is the antiderivative of x to the 1/3? Mm. Okay, yeah, you corrected yourself. 3/4 x to the 4/3. Because again, add 1 and then divide. So when it's a fraction, the fraction gets flipped. So 1/3 plus 1 is 4/3. This fraction gets flipped to be 3/4 x to the 4/3. We evaluate that from 0 to 8. So what do we do with that? Plug in 8. Minus plugging in 0. 0 to the 4/3. What is cube root of 8? 2. What does this whole thing here break down to be?
0.
0. I'm just gonna ignore that now.
Typing that in.
There's a general rule of be smarter than the calculator. 2 to the 4th, we did already, that's 16. 3 times 16 divided by 4 is also, what's 16 over 4? Hopefully we can do that multiplication. Like, yeah, you guys have done some really great exponent work today. And then 3 to the 4th, I mean 3 times 4. Should get 12 as the area under that curve. So again, what we are saying is first, what does the function x to the 1/3 look like? What does x cubed look like? Yeah. This is x cubed. How are x cubed and the cube root of x related to each other? There's a word. They're inverses. We talked with inverses. Cube root is okay. Think about like -27 would be -3 times -3 times -3. It's square roots and even roots that can't be negative. Cube roots can be, and fifth roots can be. But inverses, if I want to graph an inverse, I can flip it along the line y equals x. I'm going to sketch that in over here. Here's the line y equals x. Giving that just that general, the shape of x cubed. That's a little too arctan for my like. Let me erase and try that again. X cubed ends up looking like that. It's the flip over this line of x cubed. Sorry, this is cube root of x. Or x to the 1/3, what we just found. So between 0 and 8, that is what we have just found is we have found this area is 12. And if we did approximations, our approximations with Riemann sums would get closer and closer and closer to being that 12. Right? So looking at another one. Okay. Steps to do. Antiderivative. What's the antiderivative of 2 plus cosine x? 2x. Derivative of sine is cosine, so antiderivative of cosine is sine. From 0 to pi. Plug in pi. Minus. Plug in 0. Working this way over. What is sine of 0? Sine of 0. 0. 2 times 0? Sine of pi. Get a nice 2 pi from that one. Thinking about this in the area sense. We talked at the end of class Friday that if I have the sum of two things and I'm finding the area with that antiderivative, it's the same as saying what is the integral from 0 to pi of 2 plus what is the area from 0 to pi of cosine. So what does the graph of 2 look like? Just a line through 2. We're going from 0 to pi. So how would I find this rectangular area I blocked off? Pi times 2. Okay, what does the graph of cosine look like? Okay. I'm going to give you guys 3 points and ask one, I'll change it to 4. Which one of those is approximately where x equals pi is?
4. Or no, 2.
What is cosine of pi? -1, so it's going to be the one that's under. So we're approximately, when I find the, not even approximately, I am actually, when finding the area of cosine from 0 to pi, I'm finding that area I've just scribbled in. Why does that cancel out to be 0? Yeah, when we're above the x-axis, that's a positive area. When we're under the x-axis, that's a negative area. these are the same areas ultimately if we calculated them out, but they cancel each other because this one's positive and this one's negative, canceling each other out to be 0. So we found 2 pi from this integral plus 0 from the integral, the area of cosine x between 0 and pi. Okay. Think about the integral 0 to 4 of x minus 3 dx. What does the graph of that look like? It's an absolute value, so what do the absolute value graph looks like? A V. Where on the x-axis is the bottom of the V? Okay, I've heard -3, 0, and +3. Why surely not negative? So what we're asking if it's a 0 on the x-axis means my output is 0.
Yes, it's affecting the x.
It's the thing, what x would I plug in to make the whole thing 0? So what x would I plug in to make x minus 3 0? 3. So the point of it is at the 3. Okay, so we have that graph. We're trying to find it between 0 to 4. So we'll probably see there's triangles there. Good. Just find areas of triangles. But we aren't always going to have nice lines. So what would be great is if I could split these into 2 different functions. What is the line for the first part going down? Is the equation of that line in red?
A squared plus b squared equals c squared.
That's the thing to find a hypotenuse. I mean, if I wanted to find that line in red, it's going to have an equation of a line of an y equals mx plus b.
The white side.
It's close to y equals negative x. What is the y-intercept up here?
Is it -3? No.
+3. So the absolute value of x minus 3 is what you guys have just told me, negative x plus 3, when x is smaller than 3, right? It would continue for any x smaller than 3. What is the equation of this line? X minus 3. How are these 2 lines related to each other? They're not in, oh, they, no, they are not. They might be, no, they're not.
No, mirrored.
They're mirrored. What happens between these 2?
They're canceling each other out.
They're canceling each other out in what operation? Because like we would say 2 and 1/2 cancel each other out in multiplication. 2 times 1/2 is 1. We're gonna find the integral. We're gonna get there. They cancel each other out in what sense of like
Multiplication.
when I add them together? Or I think you might have been starting to say something of multiply by a negative. They're negatives of each other. There is a rule for the absolute value, a definition for the absolute value. The absolute value of x is this piecewise function where it's x when x is greater than 0. It returns the positive number when there's a positive inside. And it flips the sign when there's a negative inside. That's what we just used of we multiplied by negative when x was less than 3, and we kept it the same when x was greater than 3. Now, if I want to actually find this integral with our rules, we have these two functions. Where do we split between the two different functions? What x value? 3. So if I want to find the integral from 0 to 4, I'm finding the integral of 0 to 3 of which of these two? Top or bottom? The top of the negative x plus 3 plus the integral 3 to 4 of x minus 3 of the area under this curve plus the area under this curve. If I'm finding the absolute value, ultimately, things to note, when we're finding an absolute value integral, we're going to split it every spot where we would have crossed the x-axis and figure out which ones would have been negative areas and which ones would have been positive areas. But we break it down into those different functions above the x-axis ultimately. We'll see that come up again. But we have broken it up. What is the antiderivative of negative x plus 3? Negative x squared over 2 plus 3x. I'm going to plug in from 0 to 3 on that. Plus antiderivative of x minus 3. X squared over 2 minus 3x. From 3 to 4 on that one. Appropriate to put parentheses on these for what's getting plugged in with which bar. Oh, going across here, evaluating the first part, which number gets plugged in first?
Berkeley.
Okay, I have heard both now. Which one is it?
Sure.
Yeah, we do the upper minus lower. So 3 minus 0. So we'd have negative 3 squared over 2 plus 3 times 3 minus, plug in 0. We have now seen multiple in a row where the lower bound is all 0, but I do need to remind you all, it's not always 0 when we plug in the lower bound. This one, for example, when we plugged in the lower bound, we got a half. So we do always have to plug in that lower bound. A lot of times they might cancel away, but always needs to be plugged in. Okay, so that's plugging in on the first one. Second one, what gets plugged in first? 4. 4 squared over 2 minus 3 times 4 minus 3 squared over 2 minus 3 times 3. Just enough room, barely. Things that go away. Yeah, the whole 0 thing. This is again a warning with the absolute value of a lot of times looking at an upper bound and a lower bound and going, aren't those going to cancel? Notice the sign on this is negative 3 squared over 2, and the sign over here is negative 3 squared over 2. The two negatives with addition don't cancel out each other, but they rather build on top of each other. But what is then negative 3 squared over 2 minus 3 squared over 2? Negative 9 over 2 minus 9 over 2. No, and I did write these the way I did specifically. Since the negative is not part of the x, it's only the x being squared, so that negative stays. What is well, we are asking what is negative 9 halves minus 9 halves?
Or negative 9.
Yeah, negative 9 halves minus 9 halves, double to give us just that negative 9. So that's one thing we can watch out for. Negative 9. 3 times 3 plus 3 times 3. 18. 4 squared over 2. 8. And let me do 3 times 4. Oh. And negative 9 plus 18 plus 8 minus 12. It is the positive. So we have 18 plus 8 gives us 26. Minus 12 drops us back down to 14. Minus 9 drops us down to 5. I will say when I worked this problem the first time, I got a negative number at the end. And I knew that wasn't right. What about my graph would tell me that's not right?
It's all positive.
It's all positive. The fact that everything was drawn above the x-axis says, hey, the thing we're going to get at the end is entirely positive. So we got an entirely positive result of 5.
So when it goes into the negatives, it's considered negative area.
Yes, it is a very odd concept, but it's that a negative does ultimately have a meaning, and we're going to get to in a little bit. In today, we're going to talk about some net change stuff of when we think about how velocity, position, and acceleration are all related to each other, not in that order. Getting a negative result does have a meaning, like getting a negative velocity has a meaning. Getting a negative position has a meaning. So it is okay to get a negative area even in a application sense. And that is coming from just the idea of we define them as these ways. Again, applications can have negatives in certain instances. And the big reason why we do it to start out with is these are a formalization of those Riemann sums that we were doing. And remember, we talked through when we did the Riemann sums, the height, when our area was below the x-axis, our height was considered negative because it was coming from the function. So yes, it's an area under the curve. But when the curve is below the x-axis, we call it a negative area. It's a little weird because we've kind of drilled into you guys don't call an area negative, but these have more applications than just area. Hopefully that answered a question.
That makes sense because it's width or length times height, and when the height is negative and the width is positive, it's gonna be negative.
Yeah, it's that length times height, and the width is positive, height is negative. But then our brains can continue and go, but wait, we also can't necessarily have a negative length for a height. But again, applications, negatives are okay, negatives have meaning. We are setting our x-axis as our sea level, as our 0. So if we're measuring a below sea level type thing, a negative distance does have a meaning to it. All right, but yeah, anytime it's below the x-axis, we're getting a negative area from definitions, but then also applications allow for that same thing to happen. All right. Find the area of the region bounded by the graph of y equals 4 over x, the x-axis, and the vertical lines x equals 1 and x equals e. What is the original problem we're setting up? Instead of writing this out as a full sentence, how could I write this as a single expression? Integral. Which one's bigger, 1 or e? E. So this would be 1, 2, e. That's the function. 4 over x dx. This says find the area under 4 over x from 1 to e dx. Looks like here. That word is just, or that part is just part of the definition. Remember, basically every Calc 1 class gets to integrals by the end, and they talk about the integral means the area between the curve and the x-axis. And one of the first times I taught Calc 2, when we then continue on with these integrals, I had a student come to me, go, okay, so it means the area under the curve. When do we stop? So there is an answer to that, the x-axis. So the integral is stopping at the x-axis. We're between the x-axis and the curve. So that wording is there just of a, yes, this is what we're finding, but it's not really adding anything to what we're setting up.
The area, negative, and
Yeah. And we do get things that converge, diverge, which means the area exists or to a finite number, or the area doesn't have a finite number. But for these, we have a finite number. We have an answer we can get. Now, what is the antiderivative of 4 over x? I talked about how I remember which one this is. What is the typical process of taking an antiderivative when I have a power? Add 1. What is negative 1 plus 1? 0.
So we have to use ln or something, absolute value.
Yeah, so if I add 1, I get 0, and then I'd be supposedly dividing by that new exponent of 0. We can't do that. So there's a different rule for 1 over x or 4 over x or whatever number over x. And you were starting to get it, Christian. What you remember it to be?
For. Is it x to the
It's-
negative 1?
It's just absolute value of x.
Oh, because it's 1 right now.
Yes.
Cool.
So the antiderivative is 4 ln x plus c. So in our case, we're gonna have equals, not plus, equals 4 natural log of the absolute value of x from 1 to e. When we don't have bounds, plus c. When we do have bounds, no plus e. Then, what gets plugged in first? E. Minus. Plug in 1. What's the natural log of 1? 0. Because that is saying e to what power gives us 1? E to the 0 gives us 1. So this is 0. Again, plugging in that lower bound often goes away. What is the natural log of e? The natural log of 1 was 0.
1?
The natural log of e is 1. Because again, what this is saying, ln x is asking the question, e to what power gives me x? So ln of e means e to what power is e? What power would have to return the same thing? That's 1. So ln of e is 1. 4 times 1 minus 0. 4. From this, we get a few theorems from this fundamental theorem of calculus. First is the mean value theorem for integrals that says if a function f is continuous on the closed interval a to b, then there exists a number c such that the integral is the same as f of c times b minus a. This is ultimately saying is if I have this weird function, there is a value somewhere, from a to b, there is a value somewhere that would flatten out this curve and give me a rectangle that I can find the area of, right? If I'm trying to find this area, there is a height somewhere that basically, if I flattened it out, this wonky area and this rectangle would be the same. There's an average value. There's a mean value. But what ultimately we get out of that is then we can find the average value of a function using an integral. And when we say the average value of a function, we're saying, here's my weird function going up and down. We know if I want to find the average of 5 points, I add up all those values and then I divide by 5. And so I could find the average value of 5 points along here. Find the values, add them up, divide by 5. If I then wanted to find the average of 10 different values, how would I do 10 different values? I knew like I wanted to find the average of 1, 3, 7, 11, until I have 10 different values. Add them all up, divide by 10. The integral is taking all those little values in a little rectangle type sense, and then dividing by all those numbers added up together. B minus A is ultimately turning that divide by 10, divide by 5, divide by whatever into how we would do it with an integral. So if I want to find the average value, the average output I get along a curve, I find the integral and divide by B minus A. So we'll do an example. Find the average output, find the average value of 2e to the x on the interval -1 to 1. This says find the integral from -1 to 1, and then divide by this range. So how far is between -1 and 1? What is the distance from -1 to 1? 2. B minus A is 1 minus -1, or 2. We could keep the 1/2 and the 2 until the end, but there were rules for integrals we got on Friday that basically say, hey, if I'm multiplying by this number, and technically the number out here, I can multiply these two numbers together. I just can't pull an x outside the integral, but I can pull a number out. With multiplication, specifically. So what is 1/2 times 2? 1. So those can cancel, and we're really finding -1 to 1 of e to the x. What is the antiderivative of e to the x?
E to the x.
E to the x from -1 to 1. What do I plug in first?
E to the 1.
I plug in the 1 minus
E to the -1.
e to the -1. We can get an actual value from a calculator, but the average value is e minus e to the -1. Can you actually get what that is? I see the calculator in your hands. I want to talk about a little bit. What does e to the x look like? Goes to infinity. It starts out really slow and then grows really fast. I'm going from -1 to 1. This value there is that e to the -1. And this value here is e.
That's gonna be 2.350402387.
2. That's as far as we're going. Approximately 2.35. What that is ultimately telling us is if we were able to pick out every single little point along here and add them all up and divide by that infinite number of values, the average of all of them, what it averages out to, is 2.35. And actually, I have been describing this wrong because our function's not e to the x, it's 2e to the x. So these should be these outputs. So if I was trying to find the average of 2 over e to 2e, on average, the points are falling very close to 2.35. Well, my function points are very close to that output. Right. Look at another example. I have this function defined by an integral. Integral from 0 to x cosine t to t dt. And I'd really like to find what this function is at x equals 0, x equals pi over 6, x equals pi over 4, pi over 3, pi over 2, and so on. Okay. Good question. This is written correctly, I will say that. But I want to talk about some things that the integral means. Because you'll notice, one, I write the same things over and over, and then when I grade things, there are going to be certain things I am watching for every time. In 5.1, we defined certain parts of the antiderivative, like I gave you guys names for the parts of the antiderivative. It's my notebook. I want to should revisit those real fast. Talk about names. The part inside, let me just make a new function. F of x dx. The function inside has the name integrand. And the dx, the x on the dx, is our variable of integration. What the thing on the end is doing is very similar to our derivatives, right? If I said, find the derivative of 4x with respect to x, what's the derivative of 4x with respect to x? What would change if I wrote that instead? The final thing's not going to be 4t. How do I take the derivative? What variable is it saying take the derivative with respect to? This is saying take it with respect to t. This part, yeah, that t is saying with respect to t. And so that was what we used in related rates. We took the derivative as normal. Yeah, and then multiplied by a dx dt. That same thing is happening. This notation that says take with respect to x or take the derivative with respect to t is the same thing that's happening here. This t is saying I'm looking at my function with respect to t. And so we want, for our purposes, this variable and the variable of my function should always match. We will get to a point, or I should say you guys will get to a point, depending on how far in the calc sequence you need to go, where they might not match and how you handle that. It's the idea of multivariable. But for Calc 1 and even Calc 2 for Calc 2, needs, these should match. What the rest of this is saying is I'm creating a function where my upper bound is what's changing. So if I wanted to find f of 0, that means the integral of 0 to 0 of cosine t dt. Or if I want to find f of 2, that is the integral of 0 to 2 cosine t dt. So this part is creating a new function. Let me erase that for now. I also wanted to mention there were certain things I kept writing on repeat every time we're evaluating these things. One, and it goes away really fast, but one, I write the dx until we take the antiderivative. That dx from our Riemann sum is the width of our rectangle. That dx is saying I have a really small width of a rectangle. So this part, we have a width of a rectangle. This part is our height of our rectangle. This part is saying sum all of my rectangles up between -1 and 1, or between A and B. So from those Riemann sums, each part of my integral has a meaning. So it's kind of like limits, where until we've taken care of that meaning, we have to keep writing them. The dx has a meaning. It's saying take with respect to x, and also we have a tiny width of a rectangle. The function, guys aren't bad about right, or I've never seen anyone forget to write their function. And then the integral symbol is saying we're adding them all up, adding up all these rectangles. So they all have a meaning, which I wanted to stress as well. And so when you're writing things out, you need to write what you mean. Each part here means something. So now, with all those things in mind, I'm creating a new function. And this problem says, I want to evaluate at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. Ideas on how to do so. Okay, plug in each one. So integral 0 to 0 cosine t dt. What'd you say that comes out to? Why?
Because area between the same point.
Yeah, that was one of our rules from Friday. The area between the same point is 0. I could plug in 0 to pi over 6. And what's the antiderivative of cosine? Positive sign. From 0 to pi over 6. Plug in pi over 6. Sine of 0. What is sine of 0? 0. What is sine of pi over 6? That one's the 1 over 2. And I could do this again. Pi over 4. Tell me why I keep writing. What would be next? T. Then when I plug those in, get sine of pi over 4 minus sine of 0 equals square root 2 over 2. Okay. Pi over 3. Without writing out this middle part again, what do you think this is ultimately going to simplify down to? I don't want the fraction yet.
Sine
Hmm?
sine pi
Sine of pi over 3. Guys, we've been getting the sine of pi over 4, sine of pi over 6. Sine of 0. And the last one, sine of 0 to pi over 2 of cosine t dt would be sine of pi over 2. Quickly, what is sine of pi over 3? We're at 3 over 2. And sine of pi over 2. Yeah. We did this in the order of plug them in first. And then take each integral. Suppose I didn't do that. Suppose I treated this as my upper and lower bound. Cosine of t's antiderivative is what? Sine of t. Evaluated from 0 to x, I can plug in my upper bound minus my lower bound and get that sine of x. This either order idea, it is idea because it's not 1000% just this, is the second fundamental theorem of calculus. In a lot of books, this is called the fundamental theorem of calculus part 1, and the one that we did first is the part 2. They come in a bunch of different orders. But this is the second part of the fundamental theorem of calculus, and that is if I'm taking the derivative of the integral from a to x, so derivative with respect to x from a to that same variable of f of t dt, that is the same as just the function with x plugged in. This has a typo. There's supposed to be an integral here. So the derivative of the integral from, I think it's supposed to be 0 to x. 0 to x of t squared plus 1 dt. What do you think that becomes? X squared plus 1. I want to find the derivative of this one. What do you think that's going to be? Cosine 2x all to the 4th. So, yes, we would expect that. There is a problem, though. This rule basically says this thing and this thing need to match. Do they match? No. Let's take that 2x and call it u. Then if I take the derivative of 2x with respect to x, what is that? What is the derivative of 2x with respect to x? 2. This is the same as saying the derivative of u with respect to x, because 2x and u are the same. So 2 equals du dx. And then there's a bit of, this isn't really a fraction, but a lot of times we treat it as a fraction. I could technically split this and say 2 of something over du, dividing by du on both sides, equals dx. So this first substitution, 2x equals u, is going to replace out that top part, u. So I'm going to have from 0 to u. D over dx, d dx. What do I say at some point that is equal to? Where else do I have d dx is equal to something? Yeah, d dx equals to 2d du. So 2d du. The rest of that didn't get affected. Now, second fundamental theorem of calculus, do they match? Does the variable in the d du and the variable in the upper bound match? Yes. So now I can substitute in. I can substitute this u in place of t. So I'd have 2 cosine u to the 4th. And then last question. What is u in terms of x? 2x. Wednesday, we're going to get into more of this more concrete u sub idea. But anytime we change our variables, we have to go back to the original variable unless we're at a final number. We are not at a final number, so we have to go back to that original variable. The original variable was x. U is 2x by that first substitution I did. So I'd have 2 cosine 2x to the 4th. Or I would accept this, but you can also write it as 16x to the 4th. But to use this fundamental theorem of calculus where I can just, when the derivative and integral match, I can just replace that variable in. They have to match. And so I use a u substitution to make them match. Right. Now, as we finish up, one of the last things, the thing that we were talking about the most of negative areas, if the derivative is a rate of change, the derivative is the rate of change of some function, then the definite integral of the derivative is just plug in the endpoints. Very technical, but why we care is based on position, velocity, and acceleration. Which ones are derivatives of another? Velocity is position's derivative. And is the derivative of velocity. What this is saying is if I have the derivative of position, so if I'm trying to take the integral of velocity, then I'm just finding the difference between my two positions. the integral of velocity gives me my final net change. Because notice this doesn't account for what happened in the middle. But if I know how the speed of a car may be changing along the way, I take the integral of that, even if maybe the car went backwards at some point, that integral will find me the difference between where it started and where the car ended. Car might change direction at some point, but it'll give me my net change. If I want to find the total change, how do you think we'd find the total change?
Change it to plus.
Not
Absolute
quite.
Value
What absolute value?
of both of them.
I will say it's not affecting anything here. It's gonna affect this part. So total change is the the integral of the absolute value of velocity. There is unfortunately not a nice thing to just plug in because we'd actually have to evaluate that. But if I want the total change, I take the absolute value of velocity's integral. Because kind of with my walking example of I move forward and then I stop somewhere, my positive velocity integral will find that how far I move forward. And then if I go backwards, that would be a negative velocity, technically. But absolute value that it will find that how far I walk backwards and then going forward again. So total change is the integral of the absolute value of velocity. So quick example. The velocity in feet per second of a particle moving along a line is blah. What is the displacement? So displacement, is that going to be a net or total? What is displacement telling me? How far it moved over that time interval. Not adding up every little thing it does, but my particle started here and it ended here. That's net. So I would just find the integral of v of t dt from 1 to 5. Which I will leave to you guys to practice evaluating, but that gives 32 over 3 feet is the total displacement, net displacement. Second one says total distance. It gives us the word total. I'm going to quickly pull up the graph of this. I did not have that up. Our velocity function is x cubed minus 10x squared is 29x minus 20. And we want to find from 1 to 5. This function is above from 1 to 4, below from 4 to 5. If I found the absolute value of this, that flipped just that little 4 to 5 section. And so the integral from 1 to 4 would find that positive velocity section. And then the integral of the negative velocity would find the 4 to 5. So just quickly writing out what we would need to evaluate. If I found the integral from 1 to 5 of the absolute value of v of t, we saw in that graph, it switched from positive to negative at 4. So I'd have the integral from 1 to 4 of the positive version plus the integral from 4 to 5. We talked about absolute value. If I want to take something that my function is negative and take the absolute value of it, that will change the sign. So I take the integral of negative v of t. So change all the signs. And if I actually plugged in my function, we know how to take integrals of a polynomial. So again, leaving for you guys to practice, but what you should get at the end is 71. 71 sixths feet. And that very quick difference of displacement or net just gives the from one spot to where did it end difference. The total adds in the, okay, we went forward for a little bit, we went backward, and so on. And so you take the integral of each of the little pieces. And in that real fast statement, this is making that negative area positive. That absolute value where we said, hey, we're calling an area negative. We are canceling out that negative area here. And making it a positive area. All right, that wraps up 5.4. We will get to 5.5, U substitution, and more of what we did, or similar things to what we did on Wednesday. You know, post-class activity of one of those problems. You also still have one due today from Friday. So if you haven't gotten that done, that's your reminder to do that. And if you guys have any questions, let me know. Have a great couple of days. See you Wednesday.